Well, we may go to the next presentation by Fabiola Garuti and Claudio Garuti. Please, the floor is yours.
Thank you. Hi. Well, good afternoon. My name is Fabiola Garuti, and next to Claudio, we will be presenting an AHP approach to managing the risks of disaster. The range of a variable tells us between which values it can move and what type of number sequence it belongs to. It also allows for the construction of thresholds, which is very important as they enable the proper interpretation of the results obtained. In the case of risk measurement, the range must be between 1 and 0, a positive real number as expressed by this equation here, and that it is the risk, it is equal to the probability of the event occurring, which has a range between 0 and 1, times the intensity or importance of the event that also have a range between 0 and 1. So given the above, the range of the risk must necessarily be a value that also goes from 0 to 1. Any outside value from this range has no logical or mathematically valid meaning in a risk calculation. And how much is 300% of risk? So this means that the classical formula is composed by the risk equals the hazard times the vulnerability divided by the capacity, that are elements that Tatiana told us before. But again, the hazards is like an external factor of risk that's represented by the potential occurrence of an event. The vulnerability is the internal risk factor of a system exposed to the hazard, and the capacity is the capacity of the system to recover from it. So this classical formula actually is no longer compatible since there's no threshold and no restriction in the range. So we can actually get results that exceed the normalized scale between 0 and 1. So the most appropriate formula would be then that the risk actually it's the hazard times the vulnerability times 1 minus the capacity. As you may know, the two equations used to determine the stable equilibrium point with an acceptable degree of consistency are number one, the absolute proportional metric that's represented as an eigenvector. Also, the consistency, that whenever lambda equals n, then it's perfectly consistent. The level of inconsistency in the pairwise comparison matrix, and also the average of the consistency indices of a large number of randomly generated matrices. But now, how do we apply this into the risk of disaster? By calculating the disaster risk cells by hierarchy using the maximum tolerable risk associated with the zone I. This sets the threshold for determining whether the disaster risk in a given area is acceptable or not, and it's made by the multiplication between the maximum threshold for the hazard that represents the aggregated hazard assessment, and also for the maximum threshold for the vulnerability. By multiplying these two components, the equation reflects both the magnitude of the hazard and the sensitivity of the zone to those hazards. Notice that if the base risk of the cell is less than the maximum tolerable, then the cell is of a tolerable risk. So we have now a step-by-step procedure to calculate the disaster risk for various zones within a territory by considering both vulnerability and hazard models. The goal is to determine whether specific areas within a zone are at a tolerable risk. The first one would be to define the hazard model. It means to identify the types of hazards like floods, earthquakes, or hurricanes relevant to the study zone. Then to define the vulnerability and capacity models, to identify how susceptible or exposed each zone or cell is to define hazard. Then to weight the models. It means to assign weights to different hazards, vulnerabilities, and capacities according to their relative importance or influence on the overall disaster risk. Fourth, to define the evaluation grid. It means to set up a grid to evaluate the territory, determining how many zones are considered and how many homogeneous cells or sectors are within each zone. For example, we have a map here of Pucón that is in Chile, and then we settle this grid. And it's important to notice that the cells can influence the weight of the hazard in each zone. For instance, it's not the same to have a hazard of a tsunami near the coast than in the interior. So also zones defined from the risk map, the cells identify the perceived risk values in each zone, made with the equation. The fifth step would be to construct the scales for all models, to create consistent scales for evaluating hazards, vulnerabilities, and capacities across all models. And then to determine the local thresholds of the indicators of all models. This is the maximum tolerable value that each indicator can take based on its scale. Defining local thresholds provides a reference point, which is really, really important. And here are the local and global thresholds formula. For the local, is calculated as the multiplication of the consecutive levels of each indicator, scale times 2 divided by the sum of both, and the global would be the weighted sum of every local threshold. Then, seventh step, the vulnerability and capacity models. We have three equations here. The first one, it calculates the total vulnerability score for a specific model. Then the second one computes the maximum possible vulnerability by considering the local threshold. And the third one computes the total capacity score for a specific model. Then we have to calculate for each hazard model. The first equation calculates the overall hazard level for a specific cell. Then the second computes the maximum possible hazard level for a zone by summing the products of weights and local thresholds. The third one computes the base risk level for each cell. This gives a measure of the risk without considering the capacity to mitigate the impact. The fourth calculates the global risk for each cell by incorporating the capacity. And finally, the fifth that calculates the maximum tolerable risk for each zone based on the worst case hazard and vulnerability levels. The ninth step compares the calculated base risk of each cell to the maximum tolerable risk. If the base risk is lower, the cell is considered safe or tolerable. If it is equal to or exceeds the maximum tolerable risk, it indicates facing a possible disaster risk that requires management or mitigation efforts. And the 10th would be the final step is to take action or manage the situation under study by focusing in which zones and with what intensity. So the first question would be where, in which zone and which sectors or cells. Priority should be given to the cells associated with high weight indicators, starting with those whose impact value exceeds the local threshold. In other words, is to focus in which cells indicators are greater than the local threshold. Also to focus in a mandatory way for all cells whose base risk exceeds the global threshold. That would be this. So then we should have to improve the cell's capacity. And finally, how much? What to do and with what intensity? The capacity should be increased to reduce the cell's risk to the point where the global risk of the cells is less than the global threshold. And also do it for all cells with the global risk greater than the global risk threshold. Thank you very much, and you're very welcome to do any questions.
Thank you, Fabiola. Any questions? We have time for perhaps 3 questions.
I have just one question of curiosity. Thank you for the presentation. Have you tried with real data?
Hi, Anya. Yes,
Hi.
we tried in a couple of cases. I'm a professor in risk disaster management, and we use with the alums to apply to resolve problems, real problems in Chile, in different zones of Chile, applying these equations and solutions. Well, risk management need a lot of different experts. This part is the last part of the master, the master of the course, and it's where you integrate all the information you have recovered from the different point of view. I mean, geology, environmental, fluids, any kind of possible natural risks.
I have a question, Fabiola. If you could go to the beginning of your presentation, would you have the map with the at the beginning, would you said the problem? Here you have two different zones. I could assume that the redder, the worse. And it is divided by cells, by big pixels. In the next one, you have also different colors. How would this, your analysis would match or be applied on these cells? And how would they relate in the changing risks that you're implying by the heterogeneity of the space? So how would it look like?
Yes, it's a very interesting questions because that's your question right to the issue of why we have to divide zones. We have to divide zones because we may have different kind of hazard which have a different how you say impact over the territory. Okay, so you have to you may have different models, hazard models, and so you have to divide it in zones, because if you have different models, you have different metrics. This is important to understand that you cannot combine the results of zone 1 with zone 2 directly. We have another set of equation that allow you to make that combination, but at first glance you have to maintain this difference between zones, because they are affected by different not necessarily different hazard. The same hazard can have a very different impact.
Mm-hmm.
So have different importance. This showed that the hierarchy it become a holarchy. You know, the holarchy is it's a hierarchy where the alternatives feedback the mother criteria, the first level of criteria. That's how this defined holarchy, at least how Tom defined holarchy.
Well, it's only that the colors seem in this map counterintuitive, because
okay,
the redder, the worse should be closer
yes.
to the coast, maybe. Yeah.
I forgot to talk about the color. The color, right? You're right. It's showing the level of risk, the final level of risk of each cell.
Okay. Thank you.
It's a kind of GPS representation of the models.